Hello, everyone, and thank you for joining today's Climate Action webinar, Water Solutions for the Modern World. AIA California has developed the Climate Action webinar series to address various climate action topics, including zero net carbon design mandatory continuing education. We will provide links in the chat box where you can find our climate action webinars and free ZNCD on-demand education. To qualify for continuing education credit, AIA California provides the learning objectives for every webinar and includes them in the PDF presentation that can be made available online. A few quick housekeeping reminders. Today's session qualifies for 1.5 AIA HSW learning units for those who stay on and watch live. AIA California staff will report these units for you. It may take several weeks before credits are posted to your transcript. Please use the Q&A function to ask any questions for today's presenters. You can also like a question to move it to the top of the queue. Finally, cultivate a positive learning environment. AIA California sincerely acknowledges the professional expertise our volunteer presenters provide. We greatly appreciate the diversity of perspectives and recognize that items presented in today's session may elicit a variety of responses. We strongly encourage attendees to be constructive in their comments and questions to the presenters and to one another to ensure we have a session that is a productive environment and a positive learning experience for everyone. I'd now like to introduce our moderator for today's webinar. Laura Dulski, AIA, is a champion for sustainable design, assisting with project teams in integrating sustainable solutions on projects throughout California. She has designed and managed a variety of projects throughout her career, from the programmatic stages of design through budgeting and construction administration, with specialized expertise in multifamily housing, special needs schools, and mixed-use office projects, also including design of institutional transportation and healthcare facilities. And I will now hand it over to Laura. Thank you so much.
Hi, everyone. Thank you for joining today's program, Water Solutions for the Modern World. Water conservation best practices for modern buildings are evolving. Today, we invite Epic Cleantech to discuss the growing trend of on-site water reuse and why owners and leading design professionals are integrating gray water and black water recycling into new development projects. I'd like to introduce our speaker for today, Eric. Eric is the Chief Commercial Officer of Epic Cleantech and leads business development and project delivery initiatives out of their California office. With a bachelor's in environmental engineering from Ohio State University, Eric has nearly 15 years of experience in various water reuse applications, from large-scale municipal water recycling, wineries, and breweries to the Living Building Challenge products for tech campuses. Eric specializes at the intersection of technology and regulation as it pertains to enabling buildings to become net zero water users. He earlier mentioned a Mark Twain quote, which I really like: "We recognize the value of water once the well runs dry." Thank you for joining us today. Eric, please take it away.
Great. Thank you so much for the introduction, and excited to be here with you all to talk about our water systems. So again, Eric Howe, Epic Cleantech. The thrust of our focus here is really helping these buildings achieve their water goals, whether that is getting to the next level of LEED, finding the right optimal strategy on the water conservation LEED points, to really kind of design solutions around moving towards net zero water, which we'll touch more on here later in the presentation in terms of how net zero might look in different geographies around the country. So if you'll bear with me, I will get my slides up here and we'll get started. So I am looking for, I think you might see my screen now. So there's a lot of different drivers here in the on-site water reuse space, some of which are very obvious in the form of climate change. Climate change fundamentally means changing the way we think about water. But on top of that, aging infrastructure is one that doesn't always kind of rise to the surface, no pun intended, because we have all this buried infrastructure under our streets. Just to give you an example of how much infrastructure we're talking about here, there's 1.6 million miles of water and sewer mains with the average age of 45 years here in North America. So just this tremendous investment we've made, and it's coming to the end of its working life. And we're finding, in a lot of different urban areas that maybe those sewer pipes don't have the capacity for the types of vertical development different owners are looking into. So, in areas like Oakland, East Palo Alto, owners are being told, hey, we can't provide you the sanitary sewer connection. And so they're looking for alternative strategies to really be that also are more mindful in terms of how they use the water, right? And so our wastewater can be connected to our water systems, and we'll talk more about that. So that gives you a broad sense of the drivers. Obviously water scarcity throughout the West is a very big challenge that we're all hands on deck approach in terms of how we're going to adapt to what they're calling now aridification. It's no longer drought. This is the new normal that we need to be prepared for. And that's where we come in, really helping buildings adapt to that new normal in terms of being more thoughtful with water use. So there's three kind of main pillars within, the owner space in terms of why they might be doing this outside of the big macro trends. One, it's financially feasible to do so. Obviously, we understand that many projects are very pro forma driven. They have to get their financing tied together and things have to pencil out. And so we're fortunate that in many urban areas, we can hit that 3 to 10 year ROI. And we'll talk more about strategies to do that here later in the presentation. Obviously, there's sustainability. There's up to 24 lead points, and I'll walk you through that scorecard that we can help capture. There's the newest, latest and greatest sustainability certifications, Living Building Challenge. I mean, gosh, you can't have a more exciting project from a technical engineer's perspective. But then regulations, we're seeing a lot of cities now adopting ordinances that are mandating these types of systems. An example of that, we're based in San Francisco, where all buildings over 100,000 square feet, all new construction over 100,000 square feet, have to implement black water if it's a commercial building, or gray water or black water if it's a residential high rise. So there's ordinances like that in Austin, LA, and a growing number of cities around the country, as different managers of the water supply portfolio are looking at this kind of myriad approach to managing water, right? They don't want to invest all the eggs in one basket of one big municipal system. They want to have that distributed approach that brings more climate resilience to the table for the broader community. So I like to use this figure as an example of why this conversation we're having here today is so important and timely. Ultimately, there's just a tremendous amount of new development on the horizon, right? Certain people equate that to building a new New York City, basically new Manhattan every month between now and 2060. So that prompts the question, how are we going to redesign these buildings for the future? We've done it for energy in terms of these massive transformations from big centralized generation stations to more distributed energy. We've seen it in telecom, transportation, these disruptions to the initial paradigm. And that fundamental rethinking is now taking place in water. So it's a really great time to be talking about this, coupled with the fact, as designers, you can all appreciate that in some sense, you kind of get one shot to do this. It's very difficult to retrofit buildings for this type of plumbing technology. It's possible, but once those risers are plumbed to toilets, it's impractical to replumb your toilets. So maybe you could recycle for irrigation, cooling towers, but then it's going to be a very small group of buildings where that's going to make sense in terms of the added cost and complexity to do retrofit projects. So as Laura mentioned, my background is in environmental engineering. We like to follow the One Water framework, as a design practice. I mean, frankly, no matter where you live, who you are, what you do, water connects all of us. And the One Water framework is a holistic approach to managing and emphasizing that perspective that all water has value, and the benefit of every drop should be maximized within the broader water system. And so the US Water Alliance provides a really great guide to water stewards looking to adopt an integrated water management strategy. And it starts with a mindset that all water has value. And I think we can all appreciate that. That comes from the water in your reservoirs, your rivers, lakes, seas, streams, but then also the water that we use once and then discharge to our piping systems, our sewer utility. There is value in that water, and that's what we're here to talk about. It's a focus on achieving multiple benefits. It's a systematic approach, thinking more holistically within a given region about the water system. It's watershed scale thinking. It's right-sized solutions. It's partnerships, bringing outside agencies, private owners, community groups together, and then inclusion and engagement of all. And so those are kind of the fundamental principles. It provides a really nice holistic framework for thinking about these design solutions. As many cities are currently in the process of their climate resilience planning and strategy. So before we dive too deep into the technical details here, I want to set the stage with some just definitions, because this is a new practice area for many. And I will say I see some of these terms get mixed up. So black water specifically is water from toilets, and that goes for any state in the nation. It's also in the state of California includes water from kitchen uses, sinks, dishwashers. However, in certain states like Washington, that's actually dark gray water. So, it's murky, we get it. Gray water then is specifically water from our showers, from our laundry systems, from our hand washing, bathroom labs. So that gives you a sense. Black water, gray water, those are the two forms of wastewater that we primarily deal with. You also have rainwater, which is water that falls on the roof, and then stormwater that falls on the, at grade, essentially. The difference really there with stormwater is that you can see higher levels of contamination from fecal material, hydrocarbons from oil, grease, that hits the city streets. And then you have foundation drainage as well, coupled with air conditioning condensate if you're using AC systems. So, our goal is really to look at the entire portfolio of what we call alternative water supplies and figure out what is the most cost-effective way to deploying and meeting the water conservation goals. And so, traditionally, we've thought of things in a very linear way. When it comes to water use, we've designed buildings with this kind of once through model where we use the water and then we waste it, and we name that water appropriately, wastewater. Fortunately, that water is being disrupted thanks to the work of many of our colleagues. And I'll cite here International Living Future Institute. They put together the Living Building Challenge, which is now making us think more closely about that waste stream, right? What can we be doing with that? How can we do this better? And so what we're seeing now is more circular, regenerative approaches to our water systems, and we'll kind of dive into that. So, from a kind of a North Star perspective, right? What does good look like? What is the best in class building look like? Well, certainly it'd be hard to argue with doing any better than net zero water. Yes, sure, you might be able to do net positive, but let's assume that this net zero, what that means then is that we're minimizing total water consumption. We're maximizing the use of all these alternative water sources. That's our black water, our gray water, our dark gray water, storm, rain, foundation drainage. And then we're finding ways to take that wastewater and create value with it, reusing that water where we can, and then returning that water to its original source. In many projects, that may be the groundwater. So we can safely infiltrate that water back to where it came, where it will then become used once again further down the road. And then, of course, maximizing green infrastructure throughout the project. So a little bit more under the hood here, in terms of what that looks like in practice. Frankly, when you hear net zero water, you really got to think most closely about the potable water supply, right? The non-potable needs, I'm confident you can meet in most cases, but it's the potable water, right? Because we are not yet in a place where you can take black water or gray water and treat that and make that part of your drinking water supply. And so, net zero water is going to look very different from region to region, whether it, frankly, if it's even feasible, right? I'm coming to you from California. Take Southern California, for example, net zero water would be very challenging, just because we don't have the type of rainwater supplies that you might see in Northern California. And so then Northern California kind of falls somewhere in the middle, right? There's a good amount of rain in most years, not all years, but the challenge there, I worked on net zero non-potable water for Microsoft at their Silicon Valley campus. The challenge there is then you need to capture as much rainwater as you can in those few wet weather months, and then try to store that so that way you can use it through the dry months. And so what that results in is a tremendous amount of water storage, typically in buried tanks, somewhere located below the landscape system. But that does come with, of course, a cost to do so. Now, on the other spectrum, you could take the Pacific Northwest where it's raining regularly. And that's where you'll really see probably greater traction in terms of net zero water, only because it is a little bit more practical to do it there, right? Because you're getting more seasonally independent freshwater supplies from rain. Now, that comes with some regulatory red tape that really needs to be thought carefully about. And I don't have time, I don't think, today to get into all the details, but certainly there have been projects that have gone down this path. And as it can be for a lot of projects that do something for the first time, there have been some challenges along the way from the regulatory perspective. Now, these are not my projects, so I'm really not the one to speak to them, but what's going to happen is that you need to deal with regulators in terms of making them feel comfortable that this rainwater supply is safe. Where we come in is on the technology, helping, with that regulatory conversation. But, ultimately that permitting path is going to potentially change depending on which jurisdiction you're dealing with. I've heard some projects having to deal with the EPA, and essentially becoming their own water district, being like a single building. And that's really changed from region to region. I've heard of projects in the Northeast that have tried to turn the concept of, water storage reservoir or, a pond and say, well, look, our reservoir is a tank. I know it's not a very big reservoir, but that's the reservoir. And just like any other community, we're going to use that same framework. So sometimes you have to get a little creative when it comes to permitting, help connect some dots, because, oftentimes when you're doing something that hasn't been seen before, it's going to take some time to work people, bring people along to the design thinking and helping them understand why it's safe. And we totally understand that safety is always the #1 priority. So I think it's generally a good thing that we have those conversations in a very structured and organized way. Back to net zero water, in that instance, non-potable water would be supplied from harvested black water or gray water from stormwater that would be used in the plumbing fixtures that are permitted to use it. So that could be your flush fixtures, that could be your laundry systems. We're seeing increasingly the use of even recycled black water right back into the laundry system, which is now required by code in San Francisco. So again, for these larger buildings. Then you have your landscape system. Obviously, that's a great opportunity for use of non-potable water. Cooling towers, if you have cooling towers, when they're operating, that's the #1 user of water, hands down. That could be 30% of the water footprint right there. And so there's, very nice integrated approaches to serving the demands. And, our perspective is that you got to find, fit for purpose water, right? We don't need to treat everything to potable standards. Let's look at where the water is being used and then put together the kind of design and technology package that adapts to those requirements. And, for example, to get a little bit into the weeds, when you're irrigating with recycled water, you're typically your Department of Health, Department of Environmental Health, what have you, will be looking very closely at nutrient loading, right? They want to protect the surface waters, as we all do. And so we want to make sure we don't have excess nitrogen or phosphorus, depending on what the sensitive environmental conditions are. So that may trigger actually a need for additional treatment, as opposed to just using it in a toilet fixture or in a cooling tower. A cooling tower, on the other hand, may have very high sensitivity to TDS, to salts, to minerality in the water. So again, we need to think about how are we achieving those lower thresholds that might be needed so we can get the right cycles of concentration. Certain landscape features like redwood trees are very salt intolerant. So again, there may be different drivers on the water quality side that would suggest certain solution pathways, again, just depending on what the goals of the project are. And then lastly, of course, we have stormwater, and that's one that's very regionally specific. We have a lot of cities on combined sewers. In those cities during major wet weather events, very unfortunate, but a lot of our sewage basically gets displaced by all that inflow of stormwater. You get combined sewer overflows, and that water ends up, in the adjacent water bodies, be that the bay, the Puget Sound, and that's a real issue that a lot of cities are trying to grapple with, because this all comes back to that outdated infrastructure. A lot of those pipes were put in, at the turn of the 20th century. So we just didn't have the visibility and foresight, unfortunately, at that time to put an extra pipe in the ground. And now we're tasked with, oh my gosh, do we need to ripe up all the city streets to do this? I mean, that's financially infeasible in many cases. So we need to find new ways to deal with this. And that's where this on-site kind of philosophy comes in, is if we can treat all of our sewage in the building, that leaves more capacity in the city street for those storm events. So now there's, tertiary environmental benefits, but that's less, you're no longer contributing to that very specific problem, which frankly has some very specific consequences. I mean, we're talking about in some of the major storm events, billions of gallons of, untreated or partially treated sewage spilling into the city streets, into our streams and canals. So there's a lot to do there. And, fortunately, a lot of these buildings are taking part in the solution that's needed to protect our surface water, essentially. So, as we think about, so we've given you that kind of very high level in terms of at the building scale, city scale, and we're going to continue to kind of distill that down to the valves and pumps. I promise. So now we'll get to kind of the in-building systems side, right? So, there are a number of ways you can treat the water. Again, you can do gray, black. Those tend to look like very similar process systems, gray water and black water. The reason for that is that recycled water must hit a certain water quality requirement for what's called biological oxygen demand, or BOD. To achieve low levels of BOD, you need to have some form of biological treatment. Otherwise, if you were just to try to filter it, while you may be able to filter it for some time, not reducing the BOD, one would put your final water quality at risk. Also, from just a process efficiency, that puts more strain on other components, much more costly components, being your membranes. We'll talk more about kind of what a membrane is and where that fits in. But essentially, you're kind of deferring that cost to now an operating cost. Now you're replacing things much more frequently, which adds up very quickly. So, those technologies, our approach is to, again, from this one water principle, thinking about, yes, we can reclaim the water, but then what other value can we provide back to these projects? Frankly, there's a lot of organics in our in Blackwater, for example. So our approach is to strain all those organics out, dewater them, basically put it through a composting, rapid composting process that yields high quality soil amendments that can then be repurposed in the local landscape, in local ag districts. And then lastly, there's energy, right? There's a tremendous amount of heat in our wastewater. What are we doing with that? And we'll talk more about kind of our approach there. But in terms of big picture numbers here, with the technology like this, we can reduce water use by 50, 95%, in 50% being for a residential project, right? Because only so much of the wastewater can be reused due to the potable requirement. And then For commercial buildings, yeah, you can reduce your water use by 90, 95%. I'd say in a very easy manner. You can go full 100%, but that's going to require, a few extra layers of technology. So that's never where we would start the conversation. It really is just going to depend on the local needs of the project. What's the existing conditions with the sewer district? Do we have capacity? If you do, great. Let's have a backup connection there and take the extra 10% to the city. For us, we're actually spun, out of initial work with the Bill and Melinda Gates Foundation. Our co-founder is been practicing in the MEP space for 40 years here in San Francisco. So certainly that kind of building first philosophy has transcended everything we do. We recognize that, in doing on-site reuse, this is now a new technology that requires space that wasn't otherwise allocated for, it was otherwise allocated for bicycles or parking spaces. So we're very sensitive to, hey, how do we integrate this in the most strategic way possible to reduce that footprint? How do we minimize energy demand, right? This is a new energy load, so we have to be sensitive there. We can't, further the project's water goals at the expense of burning off too much energy. It needs to be simple to install. And so that's what led to this form factor. And the reason I'm showing this screen here is our opportunity we see is parking garages, right? It tends to be where all these systems are located. It's in the basement somewhere. The kind of diamond-like geometry gives us the ability to basically locate it in the back corner behind a column, right? So every parking garage, you're gonna have stalls here, and then another stall going this way at 90 degrees. You'll have usually a column right here. We can put the system on the other side of that column. That space there in almost every parking garage is just dead space. There's nothing there. Maybe there's a pallet with some storage. But for us, it's like, hey, how can we do this without taking a single parking space? Is really the design solution, and this is what we came up with. So we're really proud of that. I think, beyond just the skid, we need to think about tanks, right? Because tanks take up a lot of space. So, those tanks are needed for storage of the final treated water. It's needed for storage of the kind of incoming wastewater, which you're seeing a picture of here. We also need storage for, an eye wash station to meet OSHA requirements, chemical containment, that kind of thing. So there are some additional area needs that need to be addressed, and that's where, it all comes down to the project. How do we get creative? How do we reduce space with good design thinking? So I promised I'd talk a little bit about recovered heat, right? So an interesting statistics that I saw from the US Department of Energy, they estimated, I think this was about a year and a half ago, that 350 billion kilowatt hours of energy is lost to our sewer every year. So 350 billion, big number, engineer, what does that mean? Did the calculations, and by my calculations, that's enough energy to power every electric vehicle ever made. So tremendous opportunity, and that's just in North America. The fact of the matter is heating water takes a lot of energy, right? And we heat it up, we send it up to the building, we shower in it for 10 seconds. I don't know how long it's in the shower tray, and then it's right back down the drain. For us, it's kind of that aha moment of like, well, wait, we're already processing that water. Let's take the heat out of it, right? That's a very simple technology, heat exchanger. We can do that and basically use that heat energy to then preheat the incoming domestic hot water system, heat the incoming potable water that's going to the domestic hot water system. So in doing that, the typical figure we'll use is you can save around 24 kilowatts per day per 1,000 gallons treated. So now we have to figure out, okay, how much flow is coming out of my building. And then once you know that, you can get a rough sense of what the opportunity there is. Now, of course, that's going to depend on the distance between our wastewater connection and the domestic hot water system. If those things are adjacent, great. There's not going to be a lot of losses, but sure, there's cases where that system's up on the roof. Now we really need to think critically. Are we going to insulate the pipes? Does this still make sense due to the losses? It also depends on the types of water systems you're using, whether you're using heat pumps or boilers. So there's a lot that goes into it, but it gives you a rough sense of, yeah, that's a lot of energy that can be captured, at not a significant cost by any means. Of course, for us on the technology side, it then comes down to integrating that, sophisticated with all the right controls. So that way those things work seamlessly together, right? Your wastewater system, we need to know there's water in the tank. We need to know when the right time is to run through that system. And correspondingly on the demand side, kind of making sure everything's load balanced is really the key here. And then there's the soil amendments. And I'm realizing my slide numbering's off because I moved things around. I got really excited about energy today. So what you're seeing here, I guess not in real time, but an animation of our solids processing hub. And so, what you're seeing in that picture is that very carbon rich soil amendment that can be reused in the landscape system, which is a really great way to kind of close the loop, right? I mean, otherwise, all this material, the conventional approach is jam it down the sewer and let somebody else deal with it. And what happens is that, the sewer utility is now going to spend, a lot of money conveying it. It's going to present them some O&M challenges in terms of all the debris that stops their pumps and lift stations. And then they're going to burn a lot of energy. And the way we're managing that is to actually screen it out mechanically. And by doing so, we reduce the energy needs now on our system because we've taken all that organic matter out mechanically as opposed to using blowers and other energy systems to break it down. So it has a really big effect in terms of reducing our system's energy use, in terms of reducing the footprint of the technology, of the overall design solution. And then of course you get a nice kind of closed loop system created in terms of that soil amendment that can be, reused in so many ways. You can partner with your local parks department, right? As another amendment that they can mix in with their, compost system, for example. So there's a lot that can be done there with this. And, frankly, this isn't a conversation about soil health, but it's a really big challenge that we face, at a societal level, especially in a lot of the ag areas, right? And it's about protecting our topsoil. So this is a nice way to return that back to where we need it most in a way that brings a lot of benefit to the project as well. This is something new for us. Essentially we have a very sophisticated control system running all of our pumps, our sensors, right? We need to make sure we're monitoring water quality in real time. We need to make sure that if we are outside of any parameters, preset parameters, that we shut the system down, right? It's all about public health. In doing so, what happened there? So in doing so, I think it's going to skip on me again. Anyway, so I'll just skip ahead so it doesn't happen. In doing so, we have the ability to monitor flows at a broader level throughout the building, right? And so the opportunity we see is that, look, there's a principle, right? If you don't measure it, it's very difficult to improve, right? And so now we can integrate data from other uses around the building to capture in real time water use and then trend it. And that's the key piece here is that, we can see the trending on our landscape systems, on our cooling towers, on our potable supply, see how water is being used, and we can use that data to hopefully inform operational improvements, right? We can see from month to month, hey, something's out of alignment. We can flag that through our monitoring capabilities. We have an algorithm that monitors that and can tell the building, hey, you've exceeded your average. What's going on? You might want to check on your irrigation system. That's helping with leak detection, which is a really big deal for a lot of buildings. And then it also helps, depending on the type of facility. Let's say it's an industrial facility. They may just have an initiative to, reduce water use. Maybe it's a winery, maybe it's a brewery, right? With that data, that gives them the knowledge they need to empower their team to track down ways to reduce through source reduction. So we can deal with water conservation with technology and treatment. You can also deal with it with source reduction. And we always say, let's start with source reduction, right? That's the easy zero cost way. We just need to be very strategic and thoughtful. And then whatever's left, we'll eventually reach a limit of how much we can reduce things. From there, we need to put in place the technology solutions that'll help us get to that next level of conservation. So, as of course, with all these projects, there's a lot of technical details. There's the regulations. I'm not going to talk too much about that. That's where we can help, advise on that. What are the regulations? What should be the permitting pathway? How does this whole design integration work? We're going to get a little sample of that today. I'm going to take a quick second to talk wastewater, and I apologize in advance if I put anybody to sleep. I will try to keep it to less than 4 minutes. And then we'll get into MEP integration. I am sorry, but my slides are automatically advancing, and I don't know why. If I can freeze this. Are you still able to see my slides, Laura?
Yes, I can see them.
Okay.
It's on how it works. Yeah.
Perfect. I was able to find a pause button.
Okay.
So apologies for that. So in terms of the wastewater process, the first step here is to deal with collection of the wastewater, right? We need a supply to treat. With that in mind, many projects are doing this electively. They're doing it to further their sustainability initiatives. They're doing it due to the kind of utility savings, of course. The first step is the diversion, right? And so in that case, we typically see like a three-way valve, automated spring return. So the goal there is thinking about emergency conditions. What if we lose power? The spring return is helpful is that we send that valve a signal. So if that signal is present, obviously our system is powered up, that valve will divert flow to our collection tank. If we lose signal or if that tank is full for whatever reason, that valve closes with that fail-safe close, and flow is then shunted off and sent to the sewer. In the event we need to treat water, because again, these are demand-driven systems, right? We are treating wastewater in many cases because we have a demand for recycled water. Now, of course, we can do this in a decentralized, rural community setting. We do that too, but the kind of focus here is more on these kind of on-site water reuse systems that are really focused on water conservation. So when there's a need for non-potable water, we divert water into our tank. That water stays in the tank for 8, 12 to 16 hours, depending on the kind of design for the project. That allows us to mix the incoming flows so we get nice homogeneous conditions, because there are a range of dischargers, right? Obviously connected upstream from the building. That also allows us to buffer out these surges of supply that we're going to see in a commercial office from 9 to 5, let's just say. And then what it does is it allows us to downsize the treatment system, because we can basically use that tank as a buffering capacity. We'll fill the tank up full in the 9 to 5 hours, and then we'll pump it down overnight slowly. And so now our system can run a little bit more reliably, even keel over 24 hours at a lower flow rate, as opposed to trying to deal with the instantaneous flows. So there's some cost savings there. It does require more area from a planning perspective, but net, it tends to kind of pencil out. From there, wastewater is pumped into an aerobic tank. It can also flow via gravity if the site elevations allow for that. In that tank, we're doing the biological treatment. And so the technology we're talking about here is called a membrane bioreactor, right? Membranes are basically 1/1000th the diameter of your human hair, the pore structure. So very, very, very fine levels of filtration. And we couple that with the bioreactor, which is kind of like the microbiome in your gut. It's breaking down the organics, the nutrients in the wastewater to render it safe for irrigation uses. And then finally, we have to think about disinfection, right? Removing all the virus, protozoa, bacteria. And we do that. You get some removal with your membrane, but really the workhorse there is UV light. It basically irradiates and inactivates all of the microorganisms. You have chlorine. So typically you're looking at multiple steps of disinfection. That way you have redundancy built in. And the chlorine has the benefit of giving you residual disinfection in the distribution system in the building. You might hear a lot about Legionella, Legionnaire's disease. This is a product of the big municipal systems, the dead ends of the pipe where there is no longer chlorine or that water is stagnating. The benefit to doing this in your basement is now you know you have a chlorine disinfection residual. It gives you a lot much more certainty and protection against Legionnaire's disease as a result of that. There are other disinfection technologies. There may be preferences for other technologies like ozone or RO. You know, we can do those too. With the latter, you know, especially on RO, we try to avoid it only in that it's very energy intensive. And then also RO requires a brine stream. So, you know, for every gallon you put into an RO system, 50% becomes product and 50% goes down the drain. So for us conceptually, it's hard to kind of fathom doing all this work and then throwing 50% of that down the drain. So we try to avoid that. And then finally, we store water in a large treated water storage tank. Again, that buffers out now on the demand side, right? You're gonna have demand loads that vary throughout the day. If it's flush, connected to flush fixtures, you know, that's obviously going to be during the occupancy period, but irrigation systems might run overnight. Your cooling tower is gonna peak at 2 p.m. So that tank gives us a nice kind of storage or battery of water from which we can draw on and ensure that when we need the water, we have it, right? That's our reservoir. So there is a lot that goes into the building integration side. It touches on plumbing, it touches on electrical, obviously, it touches on HVAC. You know, HVAC in the sense of like, how is this room ventilated, right? We're always going to come to the table with the with a practical but slightly conservative approach in that, you know, and provide options. And the conservative approach here from an HVAC standpoint is considering the potential for odors. You know, while we would never expect that under normal conditions, you have to kind of plan for the worst. And so, you know, then we start to look at the HVAC system. How is this system, how is this room, how are these tanks tied into the rest of the HVAC ducting? Do we have a direct exhaust from the room, which is oftentimes preferred? That way there's no chance of odors kind of backing up into the HVAC system and, you know, ending up in the lobby, which hasn't been our project, but I've heard of that happening. Additionally, you know, if you want to be more conservative, we can put in place odor scrubbers to ensure that we're pulling all of that, what we call foul air out of the EQ tank. I mean, let's be honest, it has a odor to it, but we can manage it actively as opposed to more passive systems. So, you know, we get involved in all these different arenas. I apologize, I'm kind of running, rambling here, but we'll kind of get into the details. You know, it starts with design and permitting. What I'm showing you is what we like to put together at the start of a project, a responsibility matrix that really just details out who's on first, you know, who's doing the design work, the installation, coordinating scopes between us, the architect, the plumbing engineer, the contractor, the owner, the GC, et cetera. And there's a lot of people involved. And that's our goal, is to streamline everything. So, you know, from a permitting perspective, you know, obviously there's the design, there's doing things in Revit. If you want to BIM it out, you know, sure, we can help with that too. There's the submittals. But really, when it comes to wastewater, there's what is called an engineering report. In California, it's called a Title 22 engineering report. Title 22 are the state regs for water reclamation. And so we, you know, a report needs to be prepared, it needs to be stamped, it needs to show to the regulators now, basically proof of how we're making this project safe. And it comes in the form of what they call log removal targets. For each type of disinfection technology, you'll get certain amount of credits for removal of virus, for removal of protozoa or bacteria. And depending on your specific configuration of disinfection, there's a crediting framework. And so you need to show them, okay, here's the systems we're using, here's the dose of UV we're providing to meet the minimum threshold, or oftentimes exceed the minimum threshold by regulation. And so that engineering report is integral, obviously, to putting these systems together, but then it comes with all the integration support, right? Points of connection to the tanks, to the skids, so on and so forth. At the end of a project, you know, essentially, let's say a state project, your permitting pathways can be bifurcated, right? You'll have your building permit, for which, all the skids, eye wash stations, fire, typical building level stuff, structural anchorages, that all rolls up there. There's not a whole lot of risk in that permitting pathway. I mean, at the end of the day, it's more pumps, mechanical systems, no big deal. Where there is a little bit uncertainty currently, and we'll talk more about this, is on the Title 22 engineering side, because that permitting path actually goes to the state in many cases, with the exception of San Francisco, who manages all the permitting locally through PUC and our Department of Health. So when dealing with the state, you're dealing now with the regional water quality control boards. That permitting pathway can take some time. The fortunate thing here is if you start early, the final permit you need to build the system is the building permit. And so that's independent of really the wastewater technical permitting path. The wastewater technical permitting path with the state and the regional water quality control board is a permit to operate. So you really only need that at the end of the project. And that's why we say, hey, when you're doing DDs, now's a great time to start. Gives you plenty of time to complete the permit. In certain cities, they'll tell you 6 months. I've seen it take 2 years. So there's a lot of variability. We always just say, hey, let's be conservative. The last thing we want is wastewater holding up the building. Let's start early. Let's get that permitting going. Let's collect comments. Those comments, getting them earlier, are also helpful so that we were avoiding redesign, later on in the project. So fortunately, our team's been through it quite a bit. We kind of know where the landmines are. We know of specific design strategies that help avoid the known concerns of Regional Water Quality Control Board and Division of Drinking Water. Essentially those two work together collaboratively to make sure that these systems are safe for buildings, and they do a really great job doing that. On the plumbing side, so we'll get more into the kind of nuts and bolts, right? There needs to be a potable makeup, right, to fill the treated water storage tank in the event the system's down. I mean, there's never plan for downtime. The system might go down, intermittently for cleaning, but frankly, that's kind of addressed via the buffering tanks. But, in the event of the unforeseen, you need to have a potable backup to ensure that we have water for those connected fixtures. Now, the big concern from a permitting perspective is backflow, right? The regulators want to make sure that there's no way that this recycled water supply can backflow into our potable pipes, both in the building and of course out in the street. And so by regulation, when you're refilling that tank, you need to have an air gap, essentially. So it's a gravity supply, you shoot water down in the tank. There's no way for us now to back supply that because it's not connected to a pressurized source. So, we can help with that. There's the makeup valve obviously needs to be controlled. We need to know when the tank hits a low level. Okay, we need some fill from the city supply. There's diversion of the wastewater that we talked about, on the incoming wastewater. So that's another component that needs to be thought of and integrated into the site. There's the booster pump system that pressurizes that treated water back up into the building. You have your backflow preventer, which is required by code to protect the municipal side of things. And then you just have the interconnecting piping, right, between skids. You have floor drains, ejector pumps are a big deal, as most basements have them anyways, but certainly want to look at the drain system. Again, stuff happens. This is wastewater, plan for the worst. In the event the pipe breaks, how is wastewater going to get out of the basement of this building? That's where the drains come through, the ejector pumps. And then lastly, on the plumbing side is the signage. You do need to have signage, and I think I'm safe to say all projects, it might be a sign in the lobby just saying, hey, this building's really cool. We're using recycled water to further our environmental initiatives, right? So it just depends kind of on the use type of the building, what level of signage is needed. Do you need it at every fixture? Most times not, but it does just kind of depend on the local jurisdiction and how the building's being used. The electrical is pretty straightforward. We talked about HVAC, electrical, essentially everything's integrated onto a skid. So it really comes down to just bringing main power supply to a common source, and then all the branching's done within the skid. You do have controls. There are some field instruments that get mounted in the tanks. Each tank has, let's say, 4 sets of instruments. And so, there's some control wiring that all runs back to a control panel that's all pre-integrated, but then site installed. So, there's a lot of little details to coordinate, certainly. But we find that, if you kind of get to it at the right time, SDs, we're talking about, is there space? DDs, we're starting to really get into locking down the area. And then certainly during CDs, that's where we're detailing everything out to the whatever level of details needed for the project. So one of the other things to think about is phase development, right? We see a lot of that, big master plan developments, work that's going to happen over, frankly, over a decade. And one of the concerns we hear from owners is, well, how does this system adapt to my development plan? How does it scale with my business, right? Fortunately, there's a really elegant ways to deal with this. Our systems are all modular. Here we do put them in shipping containers from time to time. It can be on skids. For this example, it's in a shipping container, but essentially what you can do is with each successive phase of the project, you bring in that next array of treatment capacity. And there's some strategy here in terms of looking at the development phasing, the timing, understanding from the owner what their tolerance is for risk. And by risk, I mean, ultimately the lowest life cycle costs and, all in first cost is to upsize some components to serve all 3 phases of the development. So in an environment where, I'm definitely going to build these next 3 phases over 3 years, we say, no questions asked. Let's upsize, the initial screen device for all 3 phases. On the other hand, you might have a developer that says, well, this is a 20-year master plan, and I just can't get my head wrapped around investing any money into phase 3. Okay, there's a plan for that too. We can basically put in place now parallel arrays that'll each work independently as new capacity comes online. So, there's a million different ways to do this. It affects your screening, is one of the key areas to look at, your initial treatment step being the screen. It affects your tanks. Oftentimes it's more economical to build 1 larger tank than 3 small tanks. It's more space efficient to do that as well. So do we operate, 1 tank at a lower level in phase 1 and then just, create freeboard with each successive phase? Or do you want 3 tanks? That's just going to depend on the project. So there's some really great ways to manage this. And again, it's all going to come down to life cycle costs. And, we're always happy to kind of do that analysis to figure out, what's the net present value, what makes sense for the owner. Excuse me. So in terms of, where all this work is happening, I think we kind of talked about it, but, schematic design is usually a great starting point for most projects in terms of just starting to think strategically, evaluate options. This is where you're doing maybe a feasibility study, right? Let's look at the use types of the building, the program. In this phase, we might be doing a water balance, looking at the utility rates, penciling out, the annual savings, putting together ROM costs for first costs, for operating costs, and basically doing a payback assessment, right? You may be doing initial layouts to answer the question, do we have space for this? But that's kind of the extent of it. And then at this point, the system's a black box. Okay, we're going to put it in this room. We don't need any details about skids yet. But certainly in that early phase, it's very beneficial to start to get the requirements mapped out, start to get aligned on that responsibility matrix in terms of who does what. Detailed design, as I mentioned, is usually where we start to do more of the regulatory outreach. really kind of elevating the design thinking around the system, starting to kind of firm up in terms of footprints, proving to ourselves that yes, this absolutely will fit. Feasibility, we're working off the back of a napkin. Detailed design, we want to start having some firm calculations that support those initial assessments. And then obviously during CDs, that's where you're doing your construction documents, BIMing out the system, and things really start to come to life at that phase of the project. Check, see how we're doing on time. Regulatory drivers. So this is a big one because it just varies so much by state. So it's hard not knowing exactly the representation here, from local jurisdictions to states. What I will say is that, essentially San Francisco is a very much a leader in this space in terms of, on-site water reuse. They chair the Blue Ribbon Commission, which includes something like 30 other agency members, city agencies that range from Austin to LA to there's places in Minnesota, Hawaii, Oregon, Washington. I can almost guarantee Colorado, all these states have delegates to this Blue Ribbon Commission that's chaired by SFPUC. SFPUC has already done the hard work of figuring out what are the regulations pertaining to these newer systems, right? How are we going to permit in? What are the requirements? And basically what they are producing is a framework that can now be adopted by other agencies, right? So we kind of have a frontline view being headquartered in San Francisco to what is likely to transpire state by state. And undoubtedly it'll vary slightly, but the general sentiment I get from a lot of regulators is like, hey, let's not reinvent the wheel. Let's follow that framework. It's established, it's working, and then we'll start to tweak it to our needs in time. Additionally, here in the state of California, there's what's called SB 966 that was passed a few years ago that is requiring the state water board to now adopt uniform standards for the entire state. So San Francisco took care of their jurisdiction. They also, I think, supported SB 966. Senator Wiener was the signatory, or the kind of who brought this to the California Congress. He was once the head of SFPUC. So a lot of this, again, is kind of coming from San Francisco influence. The state regs, we don't know what those are going to look like yet. But again, I think the general sense of things is that it may look very similar also to San Francisco. And now we're going to have a statewide framework, which is going to be great for projects because, in its current form, you have the SF framework and the state framework. And when it comes to permitting, San Francisco is great. You know exactly what to expect. It's I wouldn't say it's prescriptive in any means, but they have a program and staff to handle this. When you're dealing with the state, I'm very sensitive to it. They have a ton on their plate, right? They're dealing with every water and wastewater system in the entire state of California. So, on-site systems are one of many project types. And so it can take time when dealing with the state. And so, we're looking at a future now with uniform standards statewide, and one that, I think is likely to be replicated. I've heard from several other states that they're in the process of adopting kind of their own sister regulations to follow this. So, as I mentioned early on, it's kind of like where we were in solar 15 years ago. We're going to see this windfall of new activity as all the state regulations now either by ordinance require it or at least support it. Whereas, even 5 years ago, you might go to do a project and they're like, you want to do what? We don't know how to permit that here. And you have to kind of work with them to help propose frameworks and bring everyone to the table. And it takes effort. The level of effort is getting less and less, and it's already so much different now than it was, in those initial wave of projects. Gosh, it's 8 years now. It's wild, time flies. So regulations, I think there's a lot of positivity as it pertains to that. And, fortunately, especially in places like San Francisco, that came with grants and incentives. We'll talk more about that when we get to the pro forma. And so here's the pro forma. So I guess it's a good time to talk about that. So, obviously, these are new costs to projects. I'd say the hidden thing to many owners that is very eye-opening is the costs of conventional utilities, right? We pay a tremendous amount actually for water and sewer utilities for a lot of the larger developments in urban areas. When you can reduce that by 90%, like that's a big deal to them. Additionally, there are ways to kind of work on the first costs. There's grants, and I have a whole list of those I can provide as a follow-up. Feel free to contact us. Connection fees is something I've always put on the table, right? Every project's going to pay a fee, or most projects pay a fee to connect to the utility, a water and sewer capacity charge. We say, well, let's be practical here, right? This building is going to use 90% less or 50% less if it's residential. Can we work together to prorate that? And fortunately, we've gone to new cities where there has been no prescriptive pathway for this, as there is in San Francisco. San Francisco is very prescriptive about what those capacity fee savings would be. You go to the new city, you show them the rules, the regs, the capacity fees, the data, the modeling, the technology, you bring all that together. And we've been successful in negotiating capacity charges, that can, I think the last one was around $750,000 first cost savings. I mean, that's paying for the system. So there's some really great incentives there to make this pencil out in the event that just the utility savings alone don't stand on themselves. So, never get discouraged by the utility savings. That's where we had to get creative. Again, the thing to note here is economies of scale are everything. I'm showing you here, I'll be totally honest, a pro forma that is unlike many others, I guess. In that one, it's a very large building, 55 stories. I think it's 750 residences. Also in one of the more expensive utility rate environments, San Francisco. So, the pro forma could look wildly different for your project. People come to us and say, hey, I've got 60,000 square foot commercial. Does this make sense? And, I could feel confidently across the board, if this is going to become a conversation about pro forma, then unfortunately it's not going to pencil out. So what are the other drivers, right? Are there other drivers? Does this make sense for you? And most projects fall somewhere in between. And we do a lot of support, and we have an entire team dedicated to this, helping look at the program of a development, putting together the water balance, like you're seeing there in the bottom left, how much water is needed for potable, for irrigation, for flush, for cooling tower, looking up the utility rates, penciling this all out, putting together the budgets to help us figure out where we sit on a cost curve. I mean, in no way do we want to be reductive in terms of making this all about cost. So that's why we love dealing with the architects. Hey, how do we want to navigate this? What are the priorities for the conversation? But we'll at least provide the data that they need to make sure that they're making sensible recommendations to the owner, right? They're never going to come back and say, well, wait, how did we get to where we are now? This doesn't make sense for me financially. If we need to, let's have that conversation early on, because we don't want to waste anybody's time. But of course, this is hardly ever all about finances, right? There are a lot of important reasons to do this, one of which, of course, includes sustainability. So, in terms of where we fit into that story in the LEED scorecard, our combined system, let's say it's a Blackwater system and we're doing all three kind of resource recovery modules, you're looking at around 24 LEED points. That comes from the water conservation side, that comes from energy, that also comes from the soil recovery piece. And so, to kind of look at that in more detail, here's a kind of draft scorecard, in terms of where those points might come from. Obviously you have your outdoor water use reduction, indoor use reduction, optimizing your process water. If there's a cooling tower, rainwater management, let's bring that into the conversation and make sure we're optimizing that resource accordingly. The building life cycle impact reduction really focuses on that soil recovery piece, right? And we're actually working now because the conventional approach is to put it in the sewer and treat it somewhere else. Because we're treating it for so much less energy, we're actually working to get greenhouse gas credits for that soil amendment. So, basically putting that carbon right back in the ground where it belongs. optimizing energy performance, that covers the thermal energy piece. Energy metering, sure, let's add some sensors to this so we can claim that credit. It's designing with resilience. Obviously, that's the conversation that we're having here today. But when you start to piece all these things together, there's additional value beyond just the water conservation credits that many people kind of overlook, right? They think just water, but it's an integrated technology and story that we're trying to tell. And there's a lot we can do to claim points for your project. So all project by project based, it's not to say that every project is going to get 24 points. It depends on the program. It depends on your utility rates. What makes sense? Does it make sense to do all 3 modules or maybe just 1? So again, the points will fall somewhere in between. I mentioned on the regulations, this is kind of just wrapping up here, and then I want to leave some time for questions. Cities with regulations, many of these are parts of that Blue Ribbon Commission I was mentioning. So if you're in any of these cities, this is a definite thing you'd want to look at. As cities adopt programs, that oftentimes comes with grant funding opportunities. An example of Austin, I think they're just finished their first year of their program. They still have a grant for optional projects. Projects will eventually become mandatory, at which time the grant conditions will be more challenging to meet, or potentially the grant goes away altogether. So it's a great time to start now, right? And one of the interesting things I hear from a lot of owners is like, fortunately, we work with a lot of great people who are like thinking they're very future driven, right? I'm going to build this building. It's going to be around, built to last, and they want it to be designed in a way that it doesn't become quickly outdated. And I think this is kind of where you can see with the regulations and with just the traction in the market, all this new activity in this space, like buildings of the future are likely to include these technologies. I'll almost guarantee some form within every new building, beyond a certain scale in most urban areas. So, they say, well, wait, why would I build a system now with or a building without it, right? I don't want to build this new building that comes online and every building on the block has, these advanced water technologies. Or gosh, what if I come back, years later and I'm now paying, significantly higher rates as a result of climate conditions. So they see this as a nice way to kind of design in a way that kind of adapts to the trends and then also protects them from rising utility rates that are undoubtedly, I think water and energy are the 2 highest raising utilities that you'll see out of any others. So a lot of activity happening there. I mentioned the grants. I'll provide a link here, and we have many others, just as many as I could get in a table. This does focus a little bit more on California. There's a few national programs here to look into. There are others, so do feel free to reach out and we'd be glad to connect you. Also, there's a lot of local businesses, especially like in LA, that help connect owners with grant funds. And that's their whole purpose, is helping to identify funding opportunities to help drive conservation, whether it's through rebates, grants, or what have you. This gives you just a quick sense of some of the projects that are taking place, or completed or taking place, a mix there. Here in the state of California, there are many others, but again, we kind of kept it California centric. I'd say, one of the really important things that we see as really our role in this space is helping to change the conversation about our water systems, right? And our connection to water. We put a lot of time into conferences, speaking events, just for Greenbuild this year. I don't know if any of y'all joined us, but we brewed a considerable amount of beer. In hindsight, probably too much beer with gray water that was sourced from the first approved gray water system in San Francisco. So that's at Related's 1550 mission development. It was the first gray water system. We're very fortunate to be a part of it. We basically said, hey, we're trying to have these conversations about why this is safe with our regulators, with our clients, design partners. What's a better way to show that it's safe than to really stand by the product and start drinking it? So we actually contracted a local brewery. We brewed, I think, 7,000 beers, which again, in hindsight, was probably too much. But we threw a great party. We had a lot of fun with it. It's been really informative to see, we sent beer to some of the people we work with, and I'll pick up on a Zoom call and I see, one of the 4 packs of beer sitting on the shelf, and they're like, yeah, this has been amazing for us too, right? Because clients come to us and say, well, hey, I see what you're talking about, but wow, this is kind of a lot to digest. How do you know it's safe? And it's like, what a better testament than standing behind your product in that way. So, it's helping to change the conversation, bring this to light, the opportunity, the safety aspect. And fortunately, I think, we're kind of having that water, Microsoft coined this, so apologies, but they, when they released their Silicon Valley campus water story, they called it their watershed moment. And they really, between them, Google, Facebook, Salesforce, there's a lot of those early adopters that took on the responsibility for putting these projects in place. And that has changed the industry, right? Because that made regulators think about, well, what are we going to do with these campuses? We have to do something, like, they're applying for permits. And that has now created a nice framework that, we can all follow those tailwinds. So water is having that watershed moment where, this is becoming more part of the dialogue, right? And when we're talking about the sustainability program and development, water is part of that analysis. And that's all you can hope for, is let's at least look at it. Let's ask the question, does this make sense? And let's also ask the question continuously, how can we do this better? And we're always looking for new, for feedback, new opportunities to help add to the conversation, create value where we can. So with that, I think I'm wrapping up. I'll share some of the recent press that we've had. If you'd like to kind of dig into this in more detail, there's a lot that's happening. I do have a little video here, but maybe I'll pause on that and turn it over to Lauren. Laura, if you'd like to ask any questions.
Okay. Thank you so much, Eric. That was a great presentation. Let's see, with a clean tech system on site, what is the permitting, inspection and monitoring involved by the governmental agencies to certify, operate, license, and health inspections required? And what cost does this add to operate?
Yeah, that's a great question. So it depends on whether it's gray water or black water, I'd say, are kind of the forking point. Most gray water, rainwater, that's local plumbing code. If you're doing black water, that goes to the state. On the O&M side, what you see in many cases that you'll have a licensed operator, in every case running a black water system, in most cases running gray. Rainwater, that's typically just done by the building managers. So there's a lot of moving parts to this, but I'll focus on the more complex pieces, because rainwater, stormwater, your building facilities team will be able to deal with that. It's simple mechanical, change out a filter, a light bulb kind of thing. For black water specifically, we'll take them in order. Basically, as part of your permit to operate the system, the state is likely to issue what they call, water reclamation rules and reporting requirements. And so you'll have to do sampling of the final treated water on some set cadence. That cadence does range, and it is changing. It used to be every day of the week. The last permit I was involved with was 3 days a week for black water, but it's going to depend on where the water is used, the scale of the facility, a lot of variables. There's a lot to that conversation. That's like a whole forking point that I'd love to dive into, because the regulations are coming down. Essentially they're formed in the 70s in the absence of all the sophisticated instrumentation we have now. So it's led to a persistent reduction. I think there will eventually be a future where it's monthly. Monthly is now what is currently typically required for a lot of gray water systems. It's a monthly check-in. So Blackwater does have higher O&M. Now that needs to be compared to first cost, right? Because gray water typically has a higher first cost due to the need to segregate your toilets from your showers. So there's some break-even point in there. What I typically advise is that smaller projects with lower utility savings optimize to OpEx. Let's find the way to reduce the OpEx. So let's go gray water if it's a residential building. But for larger buildings, larger projects, undoubtedly Blackwater is going to make more sense because that O&M cost now gets diluted into a much greater pool of utility savings. So, this is all part of that pro forma analysis we typically do during SDs. But in terms of added costs, 3 days a week sampling, that might be $100 a sample times 3 days a week. You need to have a licensed operator, so there's some labor costs there. It's all going to depend on the proximity of the project to the operator. So there's a little bit of variability, but Blackwater in general tends to have, I'd say at least maybe $20,000 to $30,000 of added OpEx if I'm trying to be safe, as compared to Greywater.
Okay. There are a lot of questions that we're asking about the various residential scales for this level of water treatment, and like for single family residential or various scales. So I believe that the answer to that would be yes, but do you want to speak to the various scales at all?
I'll do my best. So, and the reason I can only do my best is it's so regional specific. And a good example of that, I think our combined cost for water and sewer in San Francisco is like $24 per 1,000 gallons. I've looked at cities where the combined cost is $6 per 1,000 gallons. So obviously those thresholds are dramatically different in those two cities. Most coastal urban areas fall somewhere between 12 and 24, 30, 12 and 30 $12 and $30 per 1,000 gallons. In that case, the general guidance I say is like, pick up the phone and call. Again, if we're just talking ROI only, right? I think we can probably go to 10 years in some of the higher rate utility environments at 150 to 200 units. We'll get below that threshold. Now, the challenge, the hesitancy I have in answering this question is because we're not taking into account grants, those connection charges, that again upends this entire discussion. So, that's where just utility rates alone, that's where you're going to get to this. And I think that's giving you a general sense, like more than 100 units is typically needed to make this pencil on a standalone utility savings basis. Below that, we got to get really creative with grants, other funding opportunities to make this work. But single family, certainly, like I think might be a few technologies out there that do single family. That's not our space. We tend to focus on 50 units or greater is probably the main thrust of our project work, which translates to around 1,000 gallons a day or greater of treatment capacity.
Okay. Is recycled water really potable? In other words, will you drink a recycled Blackwater? I'm assuming since you made beer from it.
Who's on the call? It depends. By regulation, it's absolutely not potable. I have heard of people who will drink the water on the back end of the system if you're taking a tour. And I don't know who those people might be, but in the right audience, I mean, of course it's not permitted, but like to stand behind that quality, I mean, really it comes down to legacy permitting frameworks. And these are changing at the municipal scale. So I was involved in Pure Water San Diego, which is a project where 30% of the city's drinking water is going to come from recycled wastewater, called indirect potable reuse. LA has programs for potable reuse, whether direct or indirect. So this is the future, is drinking wastewater, and the technology is here. It just hasn't been, regulations haven't caught up with it. So that's why I say, it's very nuanced in terms of would we drink it? Like, yeah, by regulations, definitely not, but it's safe enough practically, but not advisable.
Okay, how is chlorine procured that is used in the disinfection stage? Also, what are the environmental issues, if any, or externalities with chlorine production?
Yeah, I mean, so unfortunately, chlorine does have certainly a host of environmental externalities. I don't know that I can speak to all those right now, but it really comes down by regulation. By regulation, every project in California, I don't think you'll ever be able to get away from in its current iteration using chlorine. They're going to require a certain chlorine residual as part of that permitting mandate. So, what do you do with that then? They have, there's two basic ways. You can basically bring in totes of chlorine chemical and it's dosed in with a little dosing pump. You'll have a sensor on the back end and you have an automatic pump that ramps up and down to hit the designed chlorine residual. You can also generate chlorine on site, which is pretty elegant. It adds some cost, but basically you bring in some salts and there's a host of technologies actually that allow you to self-generate. So that makes sense for the from the perspective of we're not moving hazardous chemicals around. I like it from that perspective. It really just comes down to, does that align with the owner's concerns and are they willing to maybe pay a little bit extra to do that?
Are there multiple water recycle systems on the market in a commercial scale that we can have a competitive bid?
Absolutely. Yeah, there's probably 3 or 4 different companies like us. I'd say where you'd have a hard time is I think we're the only company that combine the water treatment, the soils, and the energy. Most of our colleagues in the market are just dealing with water.
Okay. How do we deal with the total available local water budget that's shrinking every decade because of global artification? This does not stop until carbon emissions stop, and assuming that the environment survives, does this mean that coastal cities go the route that Israel has with a large implementation of desalination? We've drained our aquifers so that water is increasingly unavailable, especially for farming.
Yeah. That's like a whole nother talk. And I love that question. This is all part of the solution, right? And so I actually got my start, I've been doing water recycling in some form for 15 years. I got my start doing desal. I came to this part of the industry because I don't think that desal is the first, it should never be plan A. Desal has a lot of challenges. One, it's much more capital intensive. It's 10x the energy use. So, okay, we might be burning more fossil fuels to run that desal plant, depending on what the energy grid looks like. Additionally, you have a hazardous brine stream that needs to be managed, and there's the intake from the ocean. That's a big environmental concern. So to me, it's just not quite the most elegant solution. I think, now that said, it is probably part of many cities' adaptation plan, right? Because we need to kind of do a little bit of everything. But I always say, let's maximize out our water reclamation first, because, we can treat water with 1/10 of the energy footprint. We can treat it in a much less capitally intensive way. And, this water is otherwise, going out to the ocean. So I don't know. I think the technology's there. We've been doing water recycling for long enough now. Like, it's safe, certainly, especially for non-potable uses. Like, we're not drinking this water. So it all comes back to that thought of fit for purpose water too. Like, we don't need to treat all the wastewater to potable standards. It's adding cost, it's adding energy. Frankly, 80 to 90% of our water use is non-potable. So hopefully we have the infrastructure to treat water to a range of water qualities. Potable use for some, a short list of uses, and then we have non-potable water reclamation facilities to serve our parks, our cooling towers, our toilets. And so I think by managing, with a host of technologies ranging from water reuse, from desal to source reduction, everyone needs to think carefully about their connection and their role to play in terms of the irrigation systems that you're using, right? Because irrigation, once you put water on that land use, especially for like ornamental landscape, that doesn't come back into the system. When you're doing black water, essentially your toilet's a closed loop, right? You can almost infinitely recycle that water. But once it goes to landscape or to crops, which frankly, we need to think about our agriculture systems. That's what we were talking about offline as we were kind of doing our warm up for this session, is like, you know, that's 80% of the water use in California. And I think that's where the water scarcity issue is going to be most acutely felt, right? Because frankly, the fact of the matter is we're going to have water to drink. We may have to pay a lot more for that water. We may not have water for all of the amenities that we like to have in our buildings as a result. But really the ag is where things are going to be under the most pressure. And so trying to find that balance between, you know, our connection to water and the projects we're all working with and how it works synergistically with our friends in agriculture. I mean, gosh, our food systems, we're equally dependent on those as we are on our water systems. And I think that's why there was a quote, you know, if climate change is shark, water are the teeth, right? Because it's like, that's going to be the first thing that really, where the pain is most acutely felt first. There's going to be a lot of tertiary, secondary consequences, but you know, water may be one of the more significant.
And is rainwater and gray water compatible in terms of reuse and recharge of aquifers?
If I understand the the question correctly, I mean, all of the water supplies can be treated to a level that allow for recharge of the aquifers. I mean, frankly, you know, this approach for a lot of community systems, you know, rural communities are septic tanks. It's essentially what you're doing, you know, although with a much more primitive treatment system. So, you know, essentially you're putting it in a leach field and that slowly infiltrates that water through the soil. The soil does provide some treatment benefit and it eventually finds its way down to the aquifer. So yeah, I mean, I think generally from all wastewater perspective, with proper design and best practices in mind, that is kind of how a lot of these systems end up working.
Okay, so if you've made it this far, the AIA California staff will submit you for AIA CE credit. It may take several weeks before the credits are posted to your transcript. Today's session is being recorded and will be made available on the AIA California website, www.aiacalifornia.org. The questions that have been unanswered will be answered offline and sent out. And as always, there are more resources and tools that can be found on the AIA California's website. Thank you so much, Eric, for a great presentation. And thank you again for joining us today. We will see you at our next climate action webinar.
All right, thanks everybody.
Fantastic, Eric.